Oh yeah, that's
This talk is by Mateusz Wasilewski from Polish Academy of Sciences. We'll talk on Frucht theorem for finite quantum groups.
Yes, so thank you very much for the invitation, for the introduction. I'm afraid it's yet another talk about quantum graphs, but I will start with classical graphs and somehow try to motivate that for this particular purpose we had just classical graphs are not enough. So this will be a quantum Frucht theorem. This is joint work with Mike Brannan, Daniel Gromada, Junichiro Matsuda, and Adam Skalski. So let me start with the classical Frucht theorem. So the first basic theorem that you learn in a group theory course is the Cayley's theorem, right? That any finite group is a subgroup of some permutation group. And then you can ask, okay, can we say something more about this group? It's a subgroup of a permutation group, but what does it look like, right? And then the Frucht theorem somehow gives sort of an answer that any finite group appears as, for any finite group you can construct a graph such that this group is precisely the automorphism group of the graph, right? So finite group G, with the gamma, there is a graph such that gamma is isomorphic to the automorphism group of G.
Why is that better than knowing that it's a subgroup of a symmetric group?
No, it feels like that you have some slightly more precise information. I mean that. Yeah, it depends on the graph. It's not. Yeah, it's not objectively better. It just feels like a slightly more refined statement. Okay, and then the proof. Roughly, the idea is that from gamma you construct the. Just take first the complete graph with elements of gamma as vertices, but this is a colored graph. Because all edges are of the form G, SG for a unique element S, and then we say that such an edge is of color S, and then for each color we choose a particular graph and then replace each edge of this color with this specific graph that somehow gives us a graph with precisely gamma as the group of automorphisms. So I mean the first step is that the group of color-preserving automorphisms of this graph is gamma, and then we somehow, there is a decoloring procedure. Okay, but we're at a conference where we like to use the word quantum a lot. So of course this is what I will do next. And the first thing you can try is, you can try to look at quantum automorphism groups of classical graphs. Right, this is a natural thing, so right, so the next thing is quantum automorphism groups classical graphs. So I will not define them. You've seen them quite a bit in many talks, right? So this first you define the quantum permutation group, so which is like you have a C-star algebra generated by the entries of this universal magic unitary. So you know rows and columns are partitions of unity formed by projections, and then if you have a graph, so an extra structure, you want your magic unitary to commute with the adjacency matrix, and this is how you somehow build the quantum automorphism group of a graph. And then you can ask this question, which finite quantum groups, so you can define quantum groups, and you can ask which finite quantum groups appear as quantum automorphisms of classical graphs. You can actually ask a more general question, because these quantum permutation groups, if n is at least 4, they're actually infinite dimensional. They are compact quantum groups. They are not finite groups anymore. So you can actually ask which compact quantum groups appear as quantum automorphisms of classical graphs. This is, of course, a more difficult question, and there are like two obstacles you have to overcome. First is like the K's theorem. So the first question is which quantum groups actually appear as subgroups of quantum permutation groups. So for compact groups, there is no chance, but actually there are even finite quantum groups that are not subgroups of the quantum permutation groups. So like the smallest example I think is like dimension 24 or something like that. But then the question maybe you might ask is, you just assume that you have a finite quantum group that is a subgroup of Sm+, and you ask the question whether this can be realized as a quantum automorphism group of some graph. And then the answer is also no. And this is a question that was studied by Theo Banica and J.P. McCarthy. So there are finite quantum subgroups of Sm+ that are not quantum automorphism groups of graphs. And there are even examples that are fairly simple. So as I mentioned, there are finite quantum groups that are not subgroups of Sm+, but at least duals of finite groups are always subgroups of Sm+. This you can do. So like if gamma is a finite group, then the dual of gamma, so which is the thing that is described by the group algebra of gamma, and this embeds into some Sm+. So you can ask the question for these somehow sort of co-commutative things, so sort of almost classical in a way, or as classical as you get when you're a genuine quantum group. And then there are even counter examples here. So like one of the examples is like basically you take the simplest non-commutative group you can imagine, which is actually the simplest one, S3, and S3 plus is the dual of S3, sorry, is already a counterexample. So of course, it's a very interesting question to study, for example, for which groups can appear as quantum automorphism groups of classical graphs, but it's a very difficult question that I will not answer today. So
what's the invariant that's used to see that it's not?
I think they use like these orbitals and things like that, yeah, and then somehow imagine that there would be an action coming from the quantum automorphism group, and somehow by studying these orbitals they conclude that it's impossible. Yeah. Okay, so to overcome somehow this obstacle, we will just switch from classical graphs to quantum graphs, and then the main result will be that then everything works, as we can prove it. So what are quantum graphs? I mean, we've seen quite a few talks, so I will just briefly recall. So the setting that I will use will be the quantum adjacency matrix approach. So we have B, a finite dimensional C-star algebra. So it means that B is just, a direct sum of matrix algebras. Tau will be a trace. I should make a trace on B such that mm star is equal to identity, right? So M is the multiplication map, and M star is the Hermitian adjoint of it. So M is from B tensor B to B. Right, and then to be precise, I mean, you can write the formula that tau is the sum of traces normalized in this way. Right, so this is normalized in such a way that tau of the identity is actually the dimension of B. And then the definition is that quantum adjacency matrix is a CP map. So I use this convention that I work with CP maps. Such that M A tensor A M star is equal to A, right? So this is this crucial condition, somehow this sure idempotency condition. And then this, as Junichiro already explained in his talk, being CP under this condition is the same as saying that A is star preserving, which is sort of a reality condition. But I just like to already start from CP because then you can write cross decomposition and it's just slightly easier. Okay, so some examples. So there's always the trivial example. So it means that either you do A equal just to 0 map, which is like the irreflexive version, or you do A equal to identity, which will be the reflexive version. Then you can have the complete quantum graph. And now you will also have two versions, but I will write just one of them. So the reflexive one, just take, it's like the, sort of like a multiple of this completely depolarizing channel, right? You just map everything to the multiple of the unit. And then, in a specific case where B is just Mn, so then we can write everything out in terms of the cross operators of A, right? You could just, this has a cross decomposition, and then this corresponds to this, Weaver's definition of a quantum relation. So whenever you have a subspace in Mn, then from this subspace you build an orthonormal basis of the subspace with respect to the Hilbert-Schmidt inner product. And from this orthonormal basis you write the formula A of x is equal, okay, there's a normalization constant, sum of Vi x Vi star. Okay, so basically the difference between a general CP map and a quantum adjacency matrix is that for a CP map you can find cross operators that are orthogonal, but you will have different lambda i's here, right, for each I. So basically this condition corresponds to the fact that the Choi matrix of A is a projection, as opposed to any positive definite matrix which will have some eigenvalues. Okay, and then in his talk, Junichiro also mentioned that you can build like quantum graphs structures on finite quantum groups, which would be like the quantum KD graphs. So this is something that I want to maybe briefly discuss without going into the details. So this is a necessary tool because, I mean, it's roughly the proof of the Frucht theorem that I will state roughly follows the same procedure. So you need to have the ingredients, right? You need to have the KD graphs, because this is, I mean, this complete graph on gamma is just the KD graph where you take the generating set to be the whole group, right? So it is actually a KD graph. You use the KD graph structure, and then there will be the coloring procedure. On KD graphs, so we have gamma will be a finite quantum group. Okay, so this is described by some C-star algebra of functions on gamma, which is a finite-dimensional C-star algebra. So once again, a direct sum like that. So it fits into this framework, and tau will be the Haar measure on this. So everything fits nicely. Okay, and then a KD graph. I mean, the data of you need to build a KD graph is to have normally a subset of your group, which is symmetric, maybe doesn't contain identity, and is generating. So a subset is the same as an indicator function. And an indicator function, I mean, it should be a projection in here. Right, so A will be, the quantum adjacency matrix will be convolution by some projection. P is a projection in C of gamma. And then all the other conditions that I stated. So for example, that P is a symmetric set, somehow, closed under inverses would correspond to the condition that A should give you an undirected graph, which means precisely that A is self-adjoint. Okay, so roughly symmetric generating set. A is equal to its Hermitian adjoint, which is the same as saying that P is invariant under the antipode, whatever the antipode is. Then, the fact that that the unit does not belong to your generating set. I mean, these things don't exist, but okay. So this would correspond to the statement that the quantum graph is irreflexive, which means that the Schur product with the identity should be 0. And this is the same as saying that if you apply the co-unit to P, you get 0. And then the generating condition this corresponds to the statement. Okay, so if you have the adjacency matrix, you apply it twice, it will be convolution against P convolved with P. So it will not be an adjacency matrix anymore, but somehow the support of the projection will be the same as the space of paths of length 2. Right? If you take the A squared, you count the paths of length 2, but you have some weights, right? Because there may be more than one path. So what you need to do is somehow take a look at the support projection, and the union of these should be everything. So you take you convolve P with itself, n times, take the support projection inside the algebra, and the supremum of this should be equal to the unit. So this would be a natural connectedness condition in this case. Okay, and something that maybe I should mention is that one can define quantum automorphism groups of quantum graphs. Yes?
If I start with a classical group, do I get the Cayley graph back?
Yeah, it's just the correspondence would be just this projection will correspond to an indicator of a subset, and it will just be the usual KD graph.
But is it colored?
Sorry?
Is it colored?
No, this is just normal KD graph. There's no colors here.
Okay. Why can no flow direction also undirected?
I mean, yeah, if you have this symmetry condition, then it's undirected. This symmetry condition, then it's undirected. But yeah, you don't have to assume it. But of course, you can have it colored if you somehow take, mutually orthogonal projections and sum them up and somehow see them as separate things. And this way you can do colors. So automorphism groups. Quantum graphs. I think I'm using a lot of chalks. Okay, and how do you do that? I mean, so the quantum automorphism group of a quantum graph, I mean, it should be a thing that acts on vertices, which means on the system algebra B, and somehow commutes with the adjacency matrix. So this will be this thing. So this is like the universal compact quantum group G, such that we have an action on B. So this is a star homomorphism that somehow interacts nicely with the co-multiplication on G. Then this action should be trace preserving. And the most important thing is that it should commute with the adjacency matrix. So like so you look for a universal thing that acts on B and preserves these two things, so the trace and the adjacency matrix. And then this object exists if everything is finite dimensional. You can talk about the quantum automorphism group of the quantum graph, and then the theorem is that for each finite quantum group, there exists quantum graph G such that gamma is isomorphic to the quantum automorphism group of G. Okay, maybe I want to say a few words about the proof. If I write here, it's probably still okay. Right? So the first statement is like you want to have this colored version, right, of the Frucht theorem. Okay, and this first part of the proof actually translates to the following statement: if you have an action on this KU graph that commutes with the left action, right, with all these, somehow it sees all these colors, so it commutes with the left action, then it actually has to be the right action. And somehow this part works in the quantum setup in the same way. So the first proof is that any action So to be more precise, we just find projections P1 up to Pk that generate V or generate C of gamma. And then the statement is that if the action commutes with convolution operators defined by these, so I will write them as, A subscript P1 up to A Pk, then it has to be the right action. Or like some subgroup. Okay, and then somehow we view these projections P1 up to Pk as sort of our colors, and then we want to combine them into one object while preserving the quantum automorphism group. And the idea is that you can just use a specifically chosen classical graph and just write down the formula for the adjacency matrix explicitly. So there's so you can build the classical graph on k vertices, right? So the same k as there. We have k projections, so we have to have k projections, k vertices here, such that almost all vertices have different degrees. Right, so when you have a finite graph, one of the degrees has to repeat. It's impossible for all the vertices to have different degrees, but you can get as close as possible to it. So there's only like one repetition. Okay, and then call this adjacency matrix, something. It will be A. This will be just A without any extra thing. Okay, and then you define B prime to be B tensor Ck, and you define, A prime to be identity tensor A plus the sum of API that's not good. Maybe QI. So where QI is just the coordinate projection onto the ith coordinate. I wanted to write PI, but of course it would not be good. So QI is a projection onto the ith coordinate. And then the thing is that if you compute the degree matrix of A prime, somehow this is regular. These as somehow convolution operators are also regular. So you will somehow only see the degrees on the part of the classical graph. And if you order the degrees in such a way that somehow they match the degrees of regularity of these things, then it will mean that on your classical graph you also have somehow almost all degrees. You might have one repetition in the degree. So it means that automatically almost all of the QIs become intertwiners, and then you need to have some small extra argument that actually all of them are intertwiners, and using these projections you cut out individual APIs. So you show that if you commute with this, then you actually commute with each individual API, and then by the first part of the proof you know that this means that you come from the right action. And what's funny is that this procedure somehow, it's a simple algebraic formula, But even for the classical Frucht theorem, it seems like a more efficient procedure. You just get a smaller construction. Okay, so I still have a couple of minutes. So maybe I want to say a bit more about quantum Cayley graphs, because there is a related question whether you actually need the second step in Frucht's theorem. Because maybe it's possible that you just can find a Cayley graph that already has, your original gamma as the automorphism group, and you don't have to do anything more. And this is a question that was studied for classical groups a lot, right? So the question is, can you find? So I'm now writing like the classical question, right? Can you find a generating set S inside gamma such that gamma is already isomorphic to the automorphisms of the Cayley graph generating using this S? And basically the answer is that there are some obstructions. For example, if you have an abelian group and you have an element of order not 2, then taking the inverse will give you an automorphism that somehow doesn't come from the translation. So for abelian groups, you have to be a 2 group. This is one obstruction. There's a second class of obstructions called like a generalized dicyclic groups, which are somehow kind of similar. They also have this basically this property that somehow you can roughly do the inverse and it will give you an automorphism which is not given by the translation. And then there are some finitely many sporadic examples. And except for that, you can do it for any finite group. So it was called Watkins conjecture, and it was solved for finite groups in a series of papers by many people, so I don't remember the names. But the thing is that basically for most groups it works. Then there was also quite a bit of work on the infinite case. That was actually more recent. That was by Lehmann and Michael de la Salle. That's basically the same statement, that there are still some obstructions, like formed by the same classes of groups. But basically for infinite groups, it also works. So you can also find Cayley graphs which somehow have as few automorphisms as possible. And then we studied these questions for quantum groups. So a natural question is, what happens for finite quantum groups? So we don't have a full answer, but we have a full answer in the special case where we look at duals of finite groups. So we have an answer for duals of finite groups. And yeah, the answer is yes. I mean, excluding the classical case, so assuming that our group is actually non-abelian, right? Because if you're abelian, then a dual is also a group, and somehow it's covered by the classical result. But for non-abelian finite groups, we say that the answer is yes. Okay, so if you look at the definition of the Cayley graph, it means that you have to somehow, for a finite group gamma, you need to find a specific projection inside its group algebra. So what one does is, so take a look, so gamma, from gamma you get the group algebra, which is the direct sum over the irreducibles. and somehow you ignore the characters, so you only look at representations of dimension at these two. So only look at alpha such that d alpha is at these two. Somehow these characters are somehow too classical. They come from, you know, these abelian things, and yeah, there is somehow not enough room to do something that hasn't already been done by these people working on the classical question. And then take basically, yeah, I would just say it in words. Maybe it's easier to say it in words than write the formula down. You look at these irreducibles of dimension at least 2, and in each of them, you just take a random rank 1 projection. And you just prove that for a generic choice, you actually get what you want. So somehow, on the group algebra level, this convolution, if you choose, you know, as your basis the lambda g's, right, the shift operators, then this becomes a multiplier. And so what you want this multiplier to roughly separate the points of your group. This is the condition you need. And what you can prove is that somehow, for almost all choices, it almost separates. So it separates most of the points, and then you need some extra small argument to show that that's sufficient. Like if the group has a non-trivial center, then there's some slight extra abstraction, but it's not anything too important. Okay, so that's what I wanted to say. Thank you very much for your attention.
In your theorem, if your finite quantum group is a finite group, is your quantum graph also a graph?
Yeah, I guess so, because then B is commutative, and the construction is like you just tensor with something commutative, so you remain commutative. Yeah.
Right. Okay, then maybe I just want to mention that for the graph case, we also know this with work with David and yours. So just if I have a finite group, then I get a graph with quantum automorphism group being equal to this.
Right.
Question, what would be the analog of this for fusion categories?
I don't know, because like for fusion categories, like you typically, that would be most, at least to me, it seems that you would have to roughly work only with the central projections, right? Somehow you cannot really. That would be my that would be my impression. Somehow this is it's very crucial here to work with non-central things. So not really treat the things like the objects as like a whole, but really cutting them down into. So really need somehow the Hilbert space realization of these. Like it seems to me. So I don't know. It might be more related to like these classical questions, like, where you have actually points and you somehow do something. I don't know. Sorry.
So if there are no more questions, let's thank Mateusz again.